All right, welcome guys, welcome. The last time we spoke about the comparison test, and then we went on to look at the limit comparison test, okay? So, but our focus today is the alternating series, okay? So we're learning, and that's the beauty of Calculus 2. It gives you a lot of tools in your toolbox, and you can decide to pull them out whenever you actually need them. Okay, so right now we're learning alternating series. Now, before now, we've seen behaviors such as sometimes you have a -1, +1, -1, +1, -1, +1, continues in that manner, alternating just from the name. So can I just give a simple definition? So I'm going to say an alternating series. Okay, it's a series whose terms, it's a series whose terms alternates, okay? But alternate between what? Alternating between positive and negative and vice versa. Positive can come first, then you have a negative. It can be +1, -1, +1, -1, or -1, +1, it depends. Now, an example of such is if I have this guy, this is +1/3 -1/4 +1/5 -1/6, on and on. I can write this guy as a series, which is, we've seen how to write this type of things before now, especially when we looked at 11.1, which was the foundation. And then what if it's something like this? -3/4 +4/5 -5/6 +6/7, on and on. Okay, I can also write this guy in terms of series, but in this case, you have your alternating term. This is n/n+1. Now, if you want to check if these things are correct, when you plug in n = 1, what do you have? When you plug in n = 2, it will give you these corresponding terms. And because it's alternating, your signs are coming in clutch, okay? All right, so now let's talk about the alternating series test. Okay. The alternating series test. Now, what is the statement of this test? It's important to actually, tell us what this is all about before we start applying them, okay? So now, if we have an alternating series, suppose we have an alternating series given by, got a -1 to the power of n-1, got a bn, where your n is from 1 to infinity, b1 minus b2, b3 minus b4. Okay, this is just by listing the terms. And your bn is positive. Take note, guys, your n term is positive. If it satisfies, now these are the two special conditions, guys. Two special conditions. bn + 1. Okay, so that means that the n + 1th term is less than or equal to the nth term. Okay, in that case, this means that your bn is decreasing. And the limit of this bn goes to 0. Then the series is convergent. Okay, or perhaps let me just move this guy to the bottom. Okay. All right, so let's see, what does this alternating series test tells us about? It actually tells us pretty much that if you have an alternating series where the Bn is decreasing, okay? If the Bn is decreasing, what happens? Okay, so that's number one. Number two is that the limit of Bn equals 0. If the Bn is decreasing, what happens? That means an example of such is this, guys. You have a 1, 1/2, 1/3. This guy is decreasing. From 1 to 1/2, reduction. From this guy to this guy, we have a reduction. Okay. Now it's even beautiful when we do examples, guys. And it's beautiful. Now let's see. Now, just like the integral test, we had 3 hypotheses. Okay. So here, these are like the 2 hypotheses that must be satisfied before you come to a conclusion. Okay. Before you do come to a conclusion. Example 1. So is the alternating series in this case, it's the alternating harmonic series. This guy. Now keep in mind that we've studied harmonic series a couple of times before. And we say harmonic series diverges, right? But here now, this is not just a harmonic series, it's an alternating harmonic series. So does it actually converge? Does it actually diverge? We're going to see that in a second. Okay. Solution. So what do I have to do? I got to pick my Bn, which is this guy. Okay. What are the 2 conditions, guys? Number 1, I have to show that Bn is decreasing. Okay, so let me just write to show that if Bn is decreasing, that means that your Bn plus 1 is less than or equal to Bn. So that means your second term has to be less than your first term, third term has to be less than second term, fourth term has to be less than third term, in that order. And the second thing I got to show is that the limits as n goes larger of Bn equals 0. If these 2 conditions hold, that means the series of your Bn is convergent. Okay. So the first one is Bn decreasing. That's what we need to see. Is Bn plus 1 less than or equal to Bn? I got to check that. What is Bn plus 1? Bn plus 1 is 1 over n plus 1. What is Bn? 1 over n. So talk to me, guys. Is 1 over n plus 1 less than 1 over n? The answer is yes. Okay, for all values of n. For all values of n. Okay, for all values of n. All right. So the second thing is limit as n goes larger, Bn equals 0. Okay, let's see. All right, so let's see, limit as n goes large of 1 over n. And that is actually 0. Awesome. We really wanted to check if it was 0 and it actually was 0. Okay. So the Bn, just a little mistake here, guys. The Bn here should actually just be 1 over n. Just 1 over n. Okay. So let me correct that for my notes. All right. So these 2 conditions are satisfied. So what do we say, guys? Conclusion. The series really 1 to the power n plus 1 divided by n is convergent. by what, guys? Now, this alternating series test, it has an acronym, which we call the AST. So if you see me write AST, that is alternating series test, okay? By the alternating series test. So for now, I'm going to put a parenthesis AST. Makes sense? With respect to the AST, what are you doing? You're going to check firstly, is your BN decreasing? You got to be able to show that. Number two, is the limit of the BN equals 0. Once those two conditions are satisfied, then the series is convergent by the AST. All right. So now let's see another example. Example 2. In example 2, this is the series we're concerned about right now. Converge or diverge. We don't know, right, until we do something. Okay, solution. Firstly, identify your BN. BN is the nth term. You don't have to include the alternating parts. So that means this is n over 4 to the power of n. What is b sub n plus 1? That means wherever you have n, go plug in n plus 1. So this is n plus 1 divided by 4 to the power of n plus 1. Okay, so I got to check, is bn plus 1 less than bn? Okay, n plus 1 divided by 4 to the power of n plus 1. Okay, so now watch this. So again, question is bn plus 1 less than bn? That's what we're trying to answer. I can actually write this guy. This is n plus 1. By laws of indices, this is 4 to the power of n times 4 to the power of 1, right? This guy, this quantity is less than n plus 3n over 4 to the power of n times 4. Now, what did I do, guys? No magic, no magic, okay? So let me show you what I did. 3n is bigger than 1 since your n is greater than or equal to 1, okay? And what is your indexing? Your indexing n starts from 1. Okay, so that's what I did. And this is equal to, now this is, over here we have n plus 3n, that's 4n. Got a 4n here on top divided by 4 to the power of n times 4. 4 takes off 4. I got an n over 4 to the n. Talk to me, guys. What is this quantity? This is just bn. Amazing. So you see how we got to walk sometimes we have to walk our way through, okay? So sometimes you got to walk your way through to show that this is true. So got to see this guy right now. So this is bn plus 1 less than bn. Awesome. So the second thing I got to check is the limits as n goes large of bn equal to 0. That's a question I need to answer. Okay, let us see. Okay, limit as n goes large of n divided by 4 to the n is actually going to give you 0. Okay, so if your limit is scratchy, you want to know how to solve things like this, so which I'm not going to solve. Okay, so I can just put check. Okay, or I can just, this is true. You gotta fix, if your limit is scratchy, I mean, gotta try to remember how to do this. Okay, so since these two conditions are satisfied, conclusion, thus the series okay, this is n from 1 to infinity, converges. If the two conditions hold, the only conclusion that follows is that the guy is convergent. Okay. Now, there's another way to show that BN is decreasing or not. If this looks confusing, how am I going to think about this? I'm going to show you another way shortly, guys. And the last example I'm going to talk about, I'm going to show you, is this guy, -1 to the power of n squared divided by n squared plus n plus 1, convergent or divergent. Okay, so solution. Bn, what is my Bn? I have to be able to identify Bn. That's this part, okay? N squared over n squared plus n plus 1. Now, how do I know Bn plus 1? Whenever I have n here, plug in n plus 1. So that means I have n plus 1 all squared, right? Divided by n plus 1 all squared plus n plus 1 plus 1. So if I'm going to write this another way around, can it be something like this? N plus 1 all squared plus n plus 2. So keep in mind that I have to answer 2 questions, right? So let's start from the idea of the limits, okay? Is this guy equal to 0? I gotta check. Okay, is it equal to 0? Let's see, limit as n goes large of n squared divided by n squared plus n plus 1. Let's see, how do we do this? We divide the top and the bottom by the highest power of n, which is n squared. N squared divided by n squared plus n, right? Divided by n squared plus 1 over n. So what does this become? This becomes a limit as n goes large. On the top, you have a 1. The bottom, you have a 1 plus 1 over n plus, this should be a square, yeah. 1 over n squared. Now, as n goes large, this guy goes to 0, this guy goes to 0, you got a 1. What's happening? This limit equals 1, so that means there's an issue, okay? 1 is not equal to 0. So what does it mean? Does it mean that we can conclude from here? What it actually means is that the alternating series test cannot be used, okay? So since this guy equals to 0 is not satisfied, okay? Since this guy is not satisfied, what happens? Then the alternating series test, this means that, okay, I think I should write that way. This means that we cannot use the alternating series test. Interesting. So I got to think about something else. So that means sometimes the alternating series test may not be way to go, okay? Now, can I say this at this point? The alternating series test is just a test for convergence, okay? Remember, test for divergence, it only gives you information about divergence. It has nothing to do with convergence. The alternating series test only tells you about convergence. Keep that in mind, guys. Keep that in mind. It's an important thing to know. So if this fails, what can I do? Remember, I gotta do, so we need a different approach. Do you remember the TFD, test for divergence? I mean, that's it now. So since the limit as n goes large of this guy is different from 0, then the series diverges. What series? Okay, so let me write a series so that in the series, this guy, it diverges by what? By the test for divergence. Okay, so let me remind you, what does the test for? What does the test for divergence tells us? It tells us that when the limit of that an, or in this case now bn, when it's different from 0, then it diverges. Nice. So I'm just going to leave you guys with one more example and conclude this part. Example 4. So this is what we're attempting to answer. This is slightly different from what we did on top, but our AST can be used. That's a good thing. Is this guy convergent or divergent? Okay. Solution. Where do we start from? Again, Bn. NQ plus 1. How do I know Bn plus 1? Whatever I have, in this case, I think let me teach you another way, guys, where you can show if Bn is decreasing, okay? That way you don't have to compute Bn plus 1, because of a truth, there are some times when if you compute Bn plus 1, it's complicated. And it's going to be difficult for you to drive a conclusion. It's possible, but it could take you some time. So it's better to use the first derivative test. Do you remember that when we did the integral tests, where you showed that the first derivative of that guy is less than 0? Okay. So you can decide to. So let's do the limit first, since that will be easy. Is this guy equal to 0? That's a question. Okay. Let's see. Limit as n goes large, n squared divided by n cubed plus 1. So you divide by the highest power of n. And this guy is going to be limit as n goes large. Okay, so in this case, I got a 1 over n here, divided by 1 plus 1 over n cubed. Now, as n goes large, the guy on the top is 0, the guy on the bottom is 1. So you got a 0. Oh, so good. Done. So the second thing is Bn decreasing? Okay, right now, so I really want to teach you another approach. Okay, so let me just put a different approach in parentheses. Now we're using the first derivative test. Okay. So what do we do? What do we do? Interesting. Got to see what we do. So this is what we do, guys. We say now consider. Now, instead of your B of n, instead of writing this guy in terms of n, I got to write it in terms of x. Remember, think about integral test, okay? Consider f of x equals x squared divided by x cubed plus 1. So at the back of my mind, let me remember that I got to show that this guy is less than 0. This is where I'm driving to. Okay, so let's do this. First derivative, got to use the quotient rule. If you use the quotient rule, this guy is going to give you this guy. Got an x squared here, 3x squared here, yeah? And you take the square of the bottom. So now let's do some kind of algebra. Okay, if we do some algebra, what you have on the top is going to be x minus 2x cubed right here, yeah? It's going to be a square. Okay, so, and how did I get that? Expand this guy, minus 3x to the 4th, divided by s cubed plus 1 squared. And that gives you this guy. Now, I need to discuss this guy. Remember, when you have a rational function like this, you pay attention to what's going on the top and what's going on the bottom. On the bottom, the bottom is always going to be positive. So that means whatever has to tell me if this guy is less than 0 or not is what I have on the top. Okay, so this is how I go. This guy is less than 0 if the top, remember it's the top, right, is less than 0. Divide both sides by x. You're just going to have. Now, what value of x will make this possible? That means you need to get x all by itself, make x the subject of the formula. You have a negative x cubed minus less than -2. Divide through by a negative sign. You have a s cubed greater than 2. I need x all by itself. That means x is bigger than the cube root of 2. This is just simple algebra. So what am I going to say? F of x is actually decreasing. Now there's an interval, okay? So let me draw my number line. If this part is cube root of 2, it is decreasing for all these values here, bigger than this number, okay? So it's decreasing on, it's going to be a parenthesis, cube root of 2, infinity. What is going to be the conclusion, guys? Bn plus 1 is less than Bn when n is greater than or equal to 2. Okay, so what do I do? Both things are satisfied, guys. What is my conclusion? Conclusion is going to be that the series, what's the series again? -1 to the power of n plus 1. Okay, so that was a n squared divided by n cubed plus 1 is convergent. By what? The alternating series test. I mean, remember, the alternating series test only helps you to determine convergence, okay? So you cannot use the alternating series test and then come up with a conclusion such as it diverges. No. So that only means that if it fails, if one of those conditions fails, so what you just got to do is you got to use a different series test entirely, okay? I hope this makes sense, guys, and I hope you can attempt some beautiful problems from the textbook and on the homework. All right.